Well, first of all, I would like to welcome everyone who joined this session. It's a tutorial on the history of knowledge, graphs, main ideas. Our two presenters for today are Claudio Gutierrez, a professor at Universidad de Chile and a senior researcher at the Millennium Institute for Foundation of Data. The second speaker is Juan Sequeda, a principal scientist at data.world. At this point, I'm going to pass the mic to them.
All right, thank you very much. Well, we're going to hit the ground running here because we got 1 hour. So one of my favorite quotes, those who cannot remember the past are condemned to repeat it. I think it's very crucial for us as a scientist is to make sure that we know where we come from so we don't reinvent the wheel. And I think this area of knowledge graphs is something that we see crucial to really understand where things are coming from, because there's a lot of popularity, a lot of hype, especially after the keynote that we saw today. It's a very popular area. I'm going to go very quickly. My name is Juan Sequeda. I work for a company called data.world, which I joined after they acquired my previous company after my PhD. I come from the semantic web community. And then I'm joined by my colleague, Professor Claudio Gutierrez from Chile, who has also been kind of on both sides of the database community and the semantic web community. Let's run with this. Just a little bit of history. The history about this history is that I have personally been very interested in understanding where all the knowledge graph and the integration between the semantic web community and the database community comes from, and tracing this for a while. And I've been giving talks about this for a while, and every time learning more and more about it. And some questions I always ask the audience, hard to go do now, but raise your hand if you know about the Dartmouth workshop of the 1956. So remember, this is the place where for a whole summer, folks got together, right? Marvin Minsky, right? Cloud Shannon, a lot of people got together, and this is where AI was formed, right? At Dartmouth in the summer of 1956. Raise your hand if you know about the Japanese 5th generation project. This is one of those very important events that happened during the 80s, that the Japanese were winning on electronics, were winning on cars, and they wanted to go in on software, and they're trying to go make AI machines back in the 80s. A lot of this thing is what has influenced where we are right now. So kind of the fun thing is that Claudio and I have known each other for a while, and at Dogstool, we've been thinking about this. So for a couple of years, we've been going to Dogstool and been working on this stuff. And this is the result. This work that we're presenting here has been materialized into a paper. And so the ultimate goal of this talk is for everybody here to go read this paper. This is the paper, Knowledge Graphs, that was published this month in the Communications of the ACM, where we're provide our perspective of how knowledge and data has been integrated together at scale to generate this knowledge graphs. This tutorial really is not a survey. This is our subjective perspective, Claudio Gutierrez and Juan Sequeda's perspective of how the evolution of all these different areas have gone. So any kind of great nuggets, it's thanks to the folks that we've been able to talk to, as noted here on the screen, and any criticisms, it's all because you can all blame them to Claudio and myself. So an early vision in computer science has been to create these intelligent systems that integrate knowledge and data at scale. There's been an early vision in computer science. And one of the things that have gone popular now, since 2012 specifically, has been this area of knowledge graphs, which was introduced by Google. So what we have been doing and what we're going to go through is present knowledge graphs in this historical context, thinking about 3 areas. One is this area of knowledge and logic. Another area of data, the data management, and how knowledge and data has been intersecting over time. And we're going to go over these different eras, which roughly kind of go over these decades, but I mean, there's a lot of fuzzy lines around here. So let's start. So we're talking around the first era, which is the advent of digital age. And in this era, we start seeing 5 things. One is the automation of reasoning. We start seeing the work from Newell, Simon, and Shaw about this logic theorist, right? A way of being able to go problem-solving techniques to go do this. This is the first AI program coming up by Newell and Simon. And we see the very famous report that they have about the report of general problem-solving programs, right? By the way, all of these things, if you go find the paper and stuff and the links we showed you, you can go find these actual papers, which I really, really encourage all the people who haven't seen this to go look at this stuff. Resolution logic, right? Robinson in the 1960s, they go present this idea of how we can go automate theorem proving, right? And have all these rules of inferencing and have these unification algorithms. So resolution is one of his first approaches to go do this. And you start seeing all these algorithms, right? The DPLL algorithms, one of those first algorithms to be able to do SAT solving, right? Still, we build upon this today. Here's a very important, very interesting paper from Green and Raphael about question answering systems. And let me pause here very quickly. We talk about, look at what this introduction says, the ability to accept statements of fact and store them in its memory, the ability to search stored information efficiently and recognize items that are relevant to a particular query. Right? So I'm storing, I'm querying, and then the ability to respond appropriately to a question by identifying and presenting the answer if it is present in memory, and by deducing a reasonable logical response from relevant knowledge. So already back in the 50s, we're thinking about query answering using knowledge and be able to infer new knowledge about this. Then we have systems like ELIZA. Right? ELIZA was from Joseph Eisenbaum, MIT, right? You're talking to the computer to be able to kind of start having that interaction with the computer that can be very smart. So that's first one. How do we automate reasoning? Second, searching in complex spaces. We realized that the majority of work in early computer science was understanding how to go deal with large search spaces. And that's the essence of Dijkstra's algorithm. Right? To be able to find the shortest path is I got this big search space. How do I reduce it? And this was then generalized later on to the A-star search algorithm. So searching in spaces. Third, retrieving information from unstructured sources. This has always been kind of a quest of mankind to be able to understand what's in text. And Bertrand Raphael's, his PhD thesis is SIR, a computer program for semantic information retrieval. Right? This is, and then his advisor was Marvin Minsky. These are kind of the first kind of groundbreaking results about starting to think about how do I extract knowledge from unstructured sources. Then we go kind of into the data side, right? We have languages and systems to handle data. And so the first actual database is by Charlie Bachman, IDS, which was a network database, which is a graph database, right? We start seeing these things, and then we start getting, we have Codicil, right? The first consortium to start creating standards around this. And we get COBOL, right? COBOL is a language which is more like an English-like language. And that's really gives an inspiration for languages like SQL later on, where you actually have a language where you select from and so forth. And then finally, we have this notion of a graphical representation of knowledge. I want to represent knowledge using these bubbles and lines. And what's interesting is that all of this was done specifically to go understand natural language. And the notion of semantic networks starts to come at this time. Look, 1956 is when, with Richens, who's a botanist, is a person who presents this idea of a semantic network. Right? I refer now to a construction of an interlingua in which all the structural peculiarities of the base language are removed, and we are left what I shall call a semantic net. Right? A lot of people think that semantic networks come around from the 70s. It actually comes from a botanist in 1956. And Ross Killian is a person who takes this and really brings it into the computer science world. So just to kind of start where these are the things that we just kind of quickly went through. Let me go pass it on to Claudio to talk about some realizations and limitations.
Okay, what are we trying to convey to you? In fact, our idea behind this research and this presentation is just to try to understand why the notion, I mean the phenomena and the notion of knowledge graph is flourishing today. So the first question is, what's really new? Is there anything new, or this is just a compilation, a good integration, a kind of flourishing of all the seeds that were already planted in different areas, and now we are kind of getting the mature fruit. Okay? in general, the idea is, I mean, the question is, what's behind this hype? Is there are a lot of keywords floating around these days, and so one could think that this is just one new thing, and is there anything new? So I would like you to have these questions in mind during the whole tutorial that we are doing, okay? So the first things in this beginning era of the 50s and 60s that we call the age of the beginning of the digital age. I mean, the introduction of the computers for as a technological tool is really the idea that computers were able to perform what we did usually with our minds in terms of what's roughly designated by knowledge. And so here here arises the first question: what's really knowledge for these people? Yeah, and we can read from the papers that knowledge for these people were really solving puzzles. Yeah? So it's a very discrete way of approaching the idea of knowledge. And so here, first, I mean, as the realization is the importance of the possibility of reasoning by machines. I would say for the first time, there were previous mechanical attempts to do reasoning by automated means, but now we have really something. In fact, in this era is introduced the idea of electronic brain. I mean, the idea that you can really simulate the brain, but not really the brain, but the performance of the brain in terms of reasoning. Okay, here appear the idea of dealing with large search spaces. Remember, knowledge associated with puzzle solving, so the search spaces were a really big concern this time, and so the main algorithm for searching big spaces are from these days. Arose to the need, the importance of processing natural language. In fact, natural language was kind of an obsession of those days, and because of the technology, both software and hardware, the results were very, how to say, very discrete. And people start realizing the idea that we can represent in computers or in more formal times the classical ways of reasoning that humans have, that is drawing, that is pictures, that is a graphical representation. So in that sense, semantic nets really represents or introduce an idea that this graphical representation of knowledge in the form of nets can be implemented at a very primitive level those times. There were two limitations, and with this we will pass to the second era. First, physical limitations of hardware, and in all the directions: cost, technical, physical, yeah. And the other limitation was the gap between what we have in the representation, I mean, all the advance at the level of representation of knowledge and the implementation. Just one more thing, and can you go to the next slide, Juan? I just want to point you before we go on to this paper. This is a 1943 paper, is the famous McCulloch and Pitts paper about neural networks. So look, the idea that one can simulate biological networks by formal networks, yeah, and give a logic to those networks comes from 1943. And this idea is different from what we were thinking about. We were talking about representation of knowledge. Here, the idea is just to get a direct link of a formal device, a neural network, with its immanent logic. Yeah, this idea will go into the deep sea until for everybody, for the mainstream industry until the 2000s. Okay, so we will not talk very much about this until 20 or 40 years later. So I just want to let you know that the two streams that conform this area were already present, but this will take a lot of time to be developed in practical terms.
All right,
okay.
So to continue, so let's go on to the second era, which is the foundations of data and knowledge. So we're now going to start talking about data, knowledge, and how these things intersect over these different eras. So on the data side, what happened in the 70s, right? We have COD. COD presents the relational model, and what's very key about the relational model is this idea of data independence. And if we go back and we look at what happened with IDS, right, these network databases, is that the program and the data were tightly connected, right? And even though it was a network of graph, if I change the structure of my data, somehow my program would break. So you needed to have this, notion of, let me have an independence where it doesn't matter how my data is structured. I want to be able to go access it in terms of some abstract level. And that's what the relational model came in. So you had something that was tightly coupled, and we want to go separate this. And we're going to see how this happens. This comes in and out. What else do we have? We have Peter Shen. He presents the entity relationship model. And what's really fascinating is that at this time, they already start thinking that there's different models that we have to go integrate. And they say, look at here, the abstract. The entity relationship model can be used as a basis of unification of different views of data. The network model, the relational model, the entity set model, right? And this is a lot of the work that we see now of like, oh, a knowledge graphs is a ways of integrating different views of data. And then we start seeing the implementations of these things, right? You have the theory that comes in, and then you have System R at IBM to go implement the relational model, right? You have Stonebreaker and company doing Ingress and creating these. So you start, this is what happened on the data side. Now, on the knowledge side, we have this notion of semantic networks. And this is a very critical paper that comes out by William Woods. And this is a critique to what is a semantic network, because people start drawing literally all these bubbles and lines, and he asks himself, what does that link mean? If I say person lives in city, what does that mean? Does it mean that a person lives in a city? Does it mean that all people live in a city? And what cities? Like, we need to start formalizing what these semantic networks mean. And this gives a big rise to all the work on formalizing knowledge representation. And we see the notions of frames, right? Big important contribution by Marvin Minsky. And then John Soa also, which is really fascinating that the work of John Soa is not as known as one would expect, even though John Soa has done brilliant work here. And you can see how look at the first sentence. A database system that supports natural language queries is not really natural if it requires the user to know how the data is represented, right? A conceptual graph that can describe data according to the user's view and access the data according to the system's view. Right? So we're already talking about different abstraction layers of data. Now, what happens is that we start trying to understand how to formalize data, how to formalize all this knowledge. Pat Hayes, in his paper in the Defense of Logic, says, you know what? We can represent this in first order logic. We can represent all these semantic networks and give it semantics to it using first order logic. So on this intersection, what we start seeing is Bob Kowalski. Bob Kowalski presents predicate logic as a programming language, very famous paper that leads to the work of Prolog, right? Robert Kowalski is in Edinburgh and he travels. I had the very fortune to spend some time with Bob Kowalski and tell him stories of how he would travel and go literally drive to France and go work with Alan Coleman-Auer, who was a person the group who would actually go implement Prolog, right? There's an implementation of a logic programming language. And then we start seeing the first expert systems, right? When you have basically these rule systems that would do backward chaining to be able to go applied a lot in healthcare, right? I have these symptoms. What could be the cause of them? A very important event had happened in, I think, in the mid 70s was a workshop that was organized by Gutierrez and Minker in Toulouse. And this is where the communities of logic and the communities of data got together. And they said, wow, there is something really important here. There's this own area of research. And in this workshop, you have papers presented by Ray Ryder on the closed world databases. So closed world assumption is presented at this event. Negation is failure by Keith Clark is presented at this event. So just to jump quickly ahead, when Sparkle comes out, Sparkle didn't have negation. And the only way to go to negation was using negation as failure, which was something that was presented back in the 1970s. So here we're evolving, and let me go pass it on to Claudio.
Okay, so let's summarize the realizations. First, now we already have from the previous era the base over which this development of the relationship between data and knowledge that is at the heart of knowledge graphs is working. So first, here comes the first realization that we need the independence of representation from implementation. Yeah, and this is, I mean, quoted in the famous statement by Code that introduced this idea of representation from the logical and the physical world. The idea that we should separate and make them talk together, but keep them separate because they belong to different worlds. The second realization of this era is that semantic networks, I mean representation, the picture representation of knowledge needs formalization too, and can be formalized. At this point, recall that the formalization in mathematics, in logic, meant essentially a sequence of formulas, writing, sequential writing, formal language. But here was introduced a very nice idea that is at the very heart of the use of graphs from the knowledge perspective, is that you can represent a network can represent a set of statements, can represent knowledge in the classical sense, but by means of a graphical. It's a very nice combination of picture plus formal things. So here, we will see in the paper of this era all these efforts to introduce formal elements to the picture of the semantic networks. Yeah. And finally, people realized that really it was possible to combine logic and data by means of networks. So here the trilogy of data, knowledge, and networks is bound for the first time in a really serious way. Of course, there were two main limitations or two big limitations. Yeah, on the data side, the data models, the data formats of at the time were rather limited. Yeah, and so we will see that people start exploring different and more flexible and more richer formats. And we will see that from here, there appear one line that is the object-oriented modeling. And on the other hand, the idea of graph databases. I mean, the very idea of representing not only knowledge, but data in the form of graphs. Okay, the 80s, in fact, were the golden era of graph databases. And on the knowledge side, there was the realization that logic as such, I mean, logic here, until here, logic essentially means, since the work in the 2030s of the 19th century, form a first order logic. You know, that's what works. But first order logic is too general, too wide. Yeah, and so was the idea that we need to customize in some way the logics to the user and to practical applications. So the whole field of description logics was born in this in this era, because people understood that we need not only to reason, and reason means not only to deduce by rules, but essentially means to represent the knowledge that we as human, our community of humans have. And so description logic was installed as one of the main pillars of the development for the next 20 years.
And with that, takes us to the next era, kind of building on what Claudio just said. So on the data side, going a little bit into the details here, the world was starting to go relational, right? So now in the 80s, you actually start seeing the first companies like even Oracle, right? And Sybase and stuff, and they're taking over the relational world. And there's people saying, wait, it's not all relational. Like we need to have more flexibility. And then there's this notion of object-oriented databases come along. And what's interesting is that, remember that early in the network databases, things were tightly connected. We realized that if things changed, that the programs would break. So we have this data independence with the relational model. But then with the rise of object-oriented programming languages, we started saying, I'm writing this program, but why is everything separated from the data? So we're too separated. So we need to start getting connected again together. And this whole notion of object-oriented databases is because I want to start connecting again the program with the data. But what's interesting, you start bringing in notions as inheritance, right? Because we have this in programming languages, and we bring this into the data. We have this notion of impedance mismatches. We have about how to have identifiers between things, right? These are key things that we see now in graphs. So you have a lot of these different companies doing a lot of work on object-oriented databases. Just a handful are AT&T, HP, this is Texas Instruments. Now, the other, what Claudio was mentioning too, is this era, what we call the golden era of graph databases. And in particular, I want to bring up the work of Alberto Mendelsohn and his students. So Alberto Mendelsohn was a very important computer scientist, database theoretician who had so many contributions, and in particular in the area of graph databases, of early graph query languages, which to provide the foundation of query languages today for graphs. So Isabel Cruz and Peter Wood, right? They're still within our community, and they were the ones who presented the first query languages on recursion. We also have Mariano Conces presenting GraphLog, right? All of these things are how to put regular expressions that qualify paths on the graph. This is the foundation for the modern graph query languages. Let it be Sparkle, which has property paths, or any of these other languages like Cypher from Neo4j and so forth. They all build on this work that was presented in the 80s by Alberto Mendelsohn and his students. On the knowledge side, remember we just said that, okay, we had to go, how semantic networks, what does this mean? We can formalize it in first order logic, but first order logic is intractable. What do we do? We need to find this trade-off. And this is the very important paper by Brockman and Levesque, where they start saying, you don't need all of first order logic. You can get a subset of first order logic, and that can be tractable. You start identifying this trade-off of the computational complexity of reasoning algorithms to go do, and the expressive power of that logic language. And this gives a rise to description logics, which continues to be kind of starting this era on looking for this trade-off. And you see all these different families of languages that this was more expressive. They're all trying to go find this balance between this. You have languages like their language, the first one, KL1, Loom, which is the one from University of Southern California, Classic, which is one that came out of AT&T Labs, and so forth. Then you have other types of ways of people working on how to represent, formalize these logic languages. F-logic is another approach that brings in a lot of notions from object-oriented databases. Now, on the integration of these two things, there's these large events that occur. Remember, I talked about the Japanese. The Japanese fifth generation project comes along. As I mentioned, they were all built, the Japanese were winning on electronics and in cars, and they wanted to win on software. And their goal was to go create AI machines, software machines. And because the US was all doing Lisp, right? Lisp is going on around this time. The Europeans were using Prolog, right? Remember, Prolog comes from Kowalski and Kolbenauer. So they decided to go focus exclusively on Prolog, and basically would create AI machines and do parallel hardware to be able to go do reasoning and expert systems. And they had this goal that in the next 10 years, we're going to have automatic machine translation. They had this very, very big goals, which they did not achieve. And that's when we start entering the AI winter in the late 80s, early 90s. So what happens? The US comes along and they say, well, we can't let this happen. And they build this big consortium called MCC here in Austin, Texas, where I'm from. And this was a place that they said, look, we need to get everybody together to go compete against the Japanese when it comes to building all these AI systems, and they're focusing on doing information integration on parallel computers. The UK does the same thing. The UK has a project called the ALVI project, where they're combating against the Japanese. In the US, particularly in Austin, you start seeing these systems like Psych, right? Psych is the world's largest knowledge base and most comprehensive ontology. All of this started here in Austin because of MCC to start kind of fighting against the Japanese to go do this. You start seeing all these big rule languages, OPS5, to go build these expert systems. You have the read match algorithm, right? That is the way how we still implement today. That's for any rule-based systems. You start building systems that the connection machine. The connection machine is from Danny Hillis, which is this parallel computers to go do AI reasoning. Interesting point to connect. Danny Hillis does a lot of things after this, right? When he did his PhD, one of the companies that he founded later on was a company called MetaWeb, which built Freebase, which is the company that Google bought to go build their knowledge graph. And you start seeing data log, deductive databases, right? So we start realizing that we want to have a version of Prolog that can be worked over databases. So what happens is that we start saying, oh, we're going to go connect Prolog on top of a database, right? That's how the database, the data side, and the Prolog is the knowledge. Let's put it together. And they realize that, well, all these databases are done in a way that we have to do all these optimizations, query optimizations, but this Prolog is too separated. So how about if we create systems that tightly couple the logic and the data together? And that's where deductive databases come along. And you have the first languages called LDL by Carlos Saniolo, done also here at MCC in Austin. And you start seeing these languages like Datalog. So with that, let me pass it on quickly also to Claudio. Claudio, you're mute.
Sorry, yeah, thanks. So I will go fast because in the 80s, essentially at the level of the realization is really the idea that we have to couple logic and data at a fine level. So all the efforts of the 80s are this coupling. You can think of Prolog, you can think of the system that Juan was talking about as the efforts that pointed to coupling logic and data. And the second realization is that there is a trade-off between expressive power of logical languages and computational complexity of reasoning tasks. This trade-off is well known from years before, but here arose the need in practice to handle this trade-off. And with these realizations and with this go into deeper seas of logic and data arose the limitations. The first was that negation is really difficult to handle and was a killer for a long time. Second is that reason at large scale appeared. Usually we understood logic as, as a reasoning between a finite means 20, 60, 80, 100 variables. And so here appear logic at a really big scale. And this was a real challenge and will be one of the main challenges of the next stage when the web spread. These networks around the globe. And the third point, the third limitation was the realization that knowledge, to represent knowledge, the process of getting from the knowledge in human minds and human documents into formal things, there is a strong bottleneck over there. So there is a problem over there, and that drove to the next era that is the era that brings essentially the web.
So what happens in the 90s? We definitely have the web, and that changes a lot in our world. So actually, from the data perspective, it's fascinating. Again, Alberto Mendelsohn continues very looking into different ways of studying the web, right? There's these languages called web SQL, right? He's looking at this stuff. And there's a lot of other ways people are starting to study the computations of the web here. And then we start seeing the rise of XML, right? The entire database community over the 90s, late 90s and early 2000s, focuses so much on understanding XML and studying this. Now, one of the first standards that we start seeing when it comes to the semantic web and graphs and everything is RDF, and the actual first representation of this is back in 1998. So we start thinking about how to represent data and put metadata on the web. And because of the rise of the web, right, we're starting to go see all this semi-structured data, which is the big popular topic in this era. And object-oriented exchange model is another way to go represent semi-structured data in addition to XML. And because of the rise of so much data that we have, right, and we want to be able to go integrate data. So we start seeing all these different projects of data integration, right? This is what I call the golden era of data integration that the database community starts looking into integrating data. And you have a lot of these joint projects between companies and universities. Again, MCC is in this place. So you have the T. Simmons project from Stanford, you have InfoSleuth from MCC, you have a lot of these, so many different projects. And then because we are generating a lot of data in e-commerce, right? The web, one of the big applications of the web here is that we're starting to go e-commerce. We need to go analyze how customers are ordering things and so forth. So that's why you have all this data warehousing technology, and OLAP is a lot of the work on the data community during this time. On the knowledge side, we enter this, the AI winter, because of we have all this promise to go represent expert systems, but the Japanese, they started in 84, by early 90s, they realized they're failing and people are not getting funding anymore for this. And they sit down and realize what's going on. And they realize is that we don't have methodologies to be able to go acquire knowledge. So early on in the 90s, there's these very famous workshops called the knowledge acquisition workshops, which leads to what we know now as the conference is called ECA, right? And KCAP, ECA is in Europe, and KCAP is in the United States usually. And it's all about how do we find these methodologies to go acquire knowledge. And this is when we start people thinking about what is an ontology, and they're kind of we give the definition of an ontology to this paper by Tom Gruber, where he says an ontology is an explicit specification of a conceptualization. This is 1993. And from there, everybody starts using the word ontology. And at the end of the day, like, what does this actually mean? So we have the famous seminal papers by Michael Uschhold and Michael Gruninger on describing what are ontologies and a methodology to go present this. And we start focusing a lot on methodologies, on how to acquire knowledge and how to represent knowledge in ontologies. So in Europe, especially in Amsterdam, you have CADS, right? The knowledge acquisition and documentation structuring methodology. And the folks in Madrid, they present methontology. So there's a lot of focus on ontology engineering and also on systems to be able to go create, to facilitate this role of the knowledge engineer. These tools that the semantic web community kind of used a lot early on, Protege, was actually built in the late 90s to go represent knowledge specifically for in the areas of bioinformatics. So on the combination of these two things, deductive databases are on the rise, right? This is a very famous and seminal survey paper by Ramakrishna and Ullman on the survey of deductive databases, which I highly, highly recommend everybody take a look at right now. And we start seeing all these workshops of deductive databases going out through the 90s, of knowledge representation meets databases. And what people start doing is, like, they realize we can put knowledge on the data on the web. And this is one of those first realizations of what would become something like the semantic web. And in this case, this is Jim Hendler early on with his students and Jeff Heflin, that they want to be able to add, extend HTML to go add some ontological extensions, right? So you start seeing these, Tim Finan presents the knowledge query manipulation language, and then you start seeing this early projects in the US, the DARPA, right? The DAML project, which is about agents. And in Europe, you have OIL, right? They start representing, we have to have a way of representing, of formalizing, or having a syntax almost, a standard to represent these ontologies. So this is the realizations that we get through. Back to Claudio.
Yeah, so the 90s, essentially, you could think of the 90s as the era of the web. That means essentially scaling, networking, and semantics at big scale. Yeah, so in practical terms, the web was really becoming the space of information and knowledge, the universal space of information and knowledge, and later data. New type of data were spreading, yeah, particularly the notion of semi-structured data that flourished during this decade and will become very important later on, because the semi-structured data, notion of data, is the idea of having schemaless data, so you can depart a little bit from the kind of monolithic database system, relational database system that existed until those days. Yeah. And then this realization that network is everything you would like to have for having knowledge in a good representation. Yeah. And so people start connecting data, and then there will appear the linked data project and so on. There were, we will highlight two limitations. First, that the computational power to handle this kind of data was a challenge. Yeah, was a real challenge at these times, especially to handle graphs, big graphs. Yeah. And the other one, and this is really important, is that the pure logical technique have complexities that pose very complex challenge to scalability. So one thing, I think one important message here at the end of the 90s, we end these 40 years of development of logic and data. All the ideas, this very old idea that I mentioned during the 40s of neural networks, that during all these years was being developed by different groups in different parts in different countries and different research groups, were kind of second order or something at the side of this mainstream that we have been talking, that was essentially center of logic. So we could think of what is becoming to happen in the next years is a kind of revenge of this idea of coupling reasoning directly to models of biological networks that are called neural networks. So that's that joining of this logic plus the statistical views are what we will see in the 2000s. You are mute, Juan.
So in the 2000s, what's the big thing that happens? Big data and NoSQL, right? So we start seeing MapReduce gets presented, right? I think this is 2004 with Big Table. Then we see, I think, one of the first NoSQL systems from Amazon are presenting Dynamo. We can see that these are the big tech giants doing this because they're the ones who are dealing with all this big data. Kind of more on the academic side on the data, in the data world, is we're focusing still on data integration, and we're looking on ways of how to automate data integration and how to go focus on schema matching, on the semantic side, and creating integrating ontologies. There's all these workshops about that generate about ontology matching and schema matching. during the 90s, we had all these systems approaches to go integrate data. And I think the interesting thing is that the theoreticians come on board early 2000s and they say, well, we can start formalizing a lot of this data integration. So this is the seminal tutorial that Mauricio Lencerini has in Pods, I think it's 2001, where he presents of data integration. And you start seeing all this work on data exchange, right? Which is basically a formalization of how to go do ETL. And you start seeing these books about data exchange. So the focus, the world, the data community is doing either XML, is doing automating, how to automate data integration, understand formalizations of data integration, and then you have all these big data and NoSQLs. On the knowledge side, well, frankly, the focus are they're focusing on trying to go scale all these systems to do reasoning, and we have all these reasoner systems, right? Remember understanding that trade-off and coming with algorithms, Tableau algorithms to be able to go reason this at scale. So you have things like the fact reasoner, Hermit, Pellet. Pellet is these folks are the foundations for a company now called Stardog. But frankly, what Claudio was saying is the deep neural networks come along, the deep learning. And for the last 40 years, they've been quietly working along, and they come in and they just blow up with this particular, and this is the ImageNet paper is one of the ones that really starts shining here. And in a way, we start realizing that there's much more that we can go do with data than with just the knowledge, kind of the logic side. Now, on the integration of data and knowledge, the semantic web is the main thing that we see, right? The semantic web paper that comes in and the Scientific American article, and you start seeing these integrations of all the Europeans and the Americans starting to work together, right? We have our own different approaches. We realize we should combine them, and that does DAML plus OIL, that generates OWL, the web ontology language. You start seeing Sparkle. Linked data is this idea of it's not just about ontologies and knowledge representation, it's about actually linking the data on the web and putting things together. So this is when you start seeing about, oh, this is actually a graph and it is on a web scale. You start seeing how to extract all this knowledge and data coming from Wikipedia and representing them in this structure, in this Graphway DBpedia. And you see this creation of this the linked open data cloud. And then you also start taking these ideas of how to be able to add semantics, right? Add markup onto the web pages, people can search for them. And then you start seeing these bigger systems like Freebase, which gets acquired by Google to go create their knowledge graph. So with this, let me pass it on to Claudio.
So, okay, so we are kind of summarizing now the main trends here. Yeah. So essentially, sitting at the beginning of the 2000s, we learned to think about data knowledge in a much bigger way. Okay. The idea that reasoning is not only about small things, but is about really large scale amount of data. And as I told you, the entering of the era of neural networks due to hardware and new hardware, very clever techniques that were already known, gave rise to this idea of how we will join this data, information, knowledge at this scale. So here are the two main tools that we have, the logical tools that we have been talking about mainly, and the statistical tools that are really beginning to be relevant in this area are joining together. This is the big message of the, I mean, of the first decade of the 2000th century. So the limitations is that we don't know how to integrate this at big scale. That's one thing. And second, that the statistical methods, yeah, do not until today prove really, how to say, deduction and reasoning in the ways we expected to do. So this is something that is completely open and will give rise to the challenges that are essentially how we integrate these two lines of thought that date from really a large time ago.
So to wrap up here, so we have time for questions, where are we now, right? So in the early 2010s, this whole idea of schema.org comes along, right? And it's the irony is that schema.org is this large ontology, this large schema, which I think people could still continue to joke a little bit about psych, that they're trying to create this one thing. But guess what? That's what schema.org is. What's interesting is that they do this in a community and decentralized way. And I think the statistics are like 70% of the web now has some schema.org annotation. Wikidata has been around now, I think, for almost 5 years or longer, that now it's the natural way of representing the data. Instead of having the Wikipedia version, which is text, you have Wikidata, which is based on data, and this is all represented as a graph, as the big knowledge graph. Google comes in with their things, not strings approach in 2012, and they popularize this term called knowledge graph. And that's an important thing, that we all kind of discuss what is a knowledge graph and stuff. Our goal here is to show that there's this big history that leads us to many of these events. And one of these events is Google calling or coining this term called knowledge graphs. But this is not something that Google invented. And it's not something that's just 10 years old. The trend of graph database is growing. That is another big thing that we're seeing now. And how large company, the large tech giants, and now this is going on to so many companies, are starting to adopt all these knowledge graph technologies to be able to go deal with data and knowledge at scale. So even though knowledge graph as a term becomes popularized in 2012 by Google, here's just 60 years of all these things that we just went across that have been leading to all these efforts where we are right now. So throughout this history, we observe two important threads, right? We want to represent and manage data and knowledge at scale. And there's a diverse amount of sources of data that we want to be able to pull together. And at the end of the day, we always think about how can we make all this data and knowledge accessible to quote unquote normal users. So if we were to summarize in one paragraph, the essence of the half century that we've developed is that data was traditionally considered a commodity. Right? It's a material commodity. It's something that exists, but with no semantics. It's the bits, it's the matter, it's this thing. So data potentially can have meaning, but it doesn't have it by itself. Knowledge is something more immaterial, right? It's the thing that lives in our minds as humans, as in our language. And it has meaning, but it needs to tie it to something. So the destiny here, what we've been trying to go show you is that data and knowledge becomes bounded together through computing. And we start combining data and knowledge together. That's how we truly have meaning. And with that, thank you very much. I know this was a very quick tutorial because we've given this before. In 3 hours, we have a lot of discussion. So we have some time. I'd love to open this up for questions. And feel free to just put it in the chat.
All right, thank you very much. This has been a very exciting historical overview of what's going on over the last 50 years. It was incredible. So thank you for that. So let me ask a question. In every decade, you saw, you talked about some of the most important developments that took place. Now we've just entered a new decade. Right, we're in the 2020s now. So which do you think will be, some of the key topics in the area of knowledge graph that we should, keep our minds into?
I'll provide my answer and Claudio will have a different one. So my answer, I think, is we need to understand more the social phenomenon of integrating data and knowledge. And if we look back, so go back 20 years, we talked about knowledge acquisition bottleneck. We have methodologies. We have the knowledge engineers, right? They're all creating these expert systems. We, as the scientific and in the industry, basically have focused just on technology. Let's go automate all these things and figure it out. And kind of thinking that the humans are we don't need humans, right? They're always going to be the bottleneck in that. We now have this whole rise of human in the loop, kind of for analytics, but I think we need to just have the human in the loops, not just for analytics, but also for the integration of data. So I think that the focus is understanding how to manage humans within this whole process of creating knowledge and data together. So think about it as knowledge engineering 2.0. And the knowledge engineering 1.0 20 years ago was all about how do I bring in knowledge and create these rules and these ontologies. Now it's how do I break that knowledge and how do I figure out how to connect it to the data? So there's this going to be, I think there's going to be the rise of understanding more methodologies. And I think there's a lot of work on educating. I think so. This is my call for arms for all the academics, professors, is that I find it kind of ironic that we teach data science and we teach people Hadoop and big data, we teach them statistics and machine learning. And then what does this data mean? And people have no knowledge about data modeling, about logic. I mean, you can take 4 years in computer science and you probably, if you had 2 or 3 courses on modeling data, that's a lot. How do we expect to actually connect data and knowledge together if we're not even teaching people how to model data? So I think there's a lot of interesting work on the social aspects, methodologies to do this, and also academic and curriculums that need to be adapted. That's my perspective. Claudio, feel free to disagree.
Just to add a small thing, because I think we don't have very much time. So I think I will mention 2 challenges especially for researchers that are beginning to work on this. First, that classical database or data researchers work in a world where data was collected with a purpose. We know about data. I mean, the database were about data that have a very precise objective. I think one of the big challenge is to develop a whole data perspective for data that we don't know what means. We don't know how it was collected. We don't know the purpose of the data. And that kind of data now is bigger than the other one. And on the knowledge side, I think we have to rethink what knowledge means. Usually we associate knowledge with classical logic, with formalization. And the statisticians since the 19th century were telling us that knowledge, there is something more in data than logic. And now we realize that it's not that only that, it's that other formats, other ways of conveying knowledge by images, by sound is, taking place because of the hardware and technology that advance. So I think there is a real challenge for us to take away, to wash our brains in the sense that knowledge has different meaning of what it meant during all these years.
Great, thank you. I think we have time for maybe one more question from the audience. If there is one.
Can I ask something? From Christophitis Vasilis. So I wrote a comment on the chat. I think my humble opinion, what is missing from the picture you presented is all the work of John Milopoulos around semantic nets that, if I'm not wrong, was one of the first languages that introduced it, properties as first-class citizen modeling constructs compared to all the other languages that you have presented, if I remember very well. But this is just a comment. My question is related to the remark of Claudio, the last remark, is what is the substance of knowledge about the data nowadays? So when all this knowledge representation wave started, which includes also semantic nets, semantic modeling of database, object-oriented, etc., the underlying assumption is that we need symbolic ways to represent knowledge. And nowadays, the semantics of all this multimodal data that are available, on the web, comes from a vectorial representation. So it's more about a numerical representation of the data, and it's not anymore a symbolic one. So how we can actually leverage what has been done, over the last 30 at least years, or in your surveys more than 50 years of work. Okay. Essentially is the question that Claudio brought previously on the merge between statistical learning and knowledge representation.
The only remark I will add to Vasilis' question or comment is that, I mean, we are getting back the analog techniques and the analog world that was thrown away by the digital procedures in the 50s. Yeah. And so I think that's a very interesting comeback that I think will have a lot to say to us that work essentially in the discrete world. I think there is a whole open world there, and I have no idea. I cannot answer, I mean, Vasilis' concern about how this will happen, but I think that's the real challenge today.
Thank you, Claudio.
All right, and thank you everyone for attending this this meeting. We're already a few minutes past time. Of course, there are social rooms. You can catch the speakers. There's emails if you're going to ask them more questions. So enjoy the rest of your conference, and thank you once again for attending.
Thank you, everybody. And if you want more information, you can find the longer paper at the Communications ACM this month.
And of course.
All right.